Welcome back to the deep dive. Today we have a topic that I think is going to resonate with a lot of you. We are looking at a scenario that is, well, it's playing out in boardrooms and engineering dens, basically everywhere right now.
Okay.
It's what the source material calls the morning after scenario.
Right, the morning after. It sounds a bit dramatic, but I mean, in software engineering, that is usually when the real headaches start.
Exactly. So I want you to picture this. You've just seen this incredible demo, right? The chief technology officer stands up, they hook up this massive AI brain.
GPT-4, Claude, pick your poison.
Yeah, pick your poison.
Yeah.
They hook it into the company's private data, and they ask it something like, what is our vacation policy? And the AI just answers perfectly. It's magic. The CEO is clapping.
The investors are drooling.
Right, the investors are drooling. It feels like the future has finally arrived.
Yeah, everyone leaves the room thinking, we did it. We solved enterprise search.
Right. And then comes the rollout. Monday morning, real users are asking real questions. And suddenly that magic oracle, it starts acting kind of drunk.
Drunk? Or, honestly worse, it acts confident and wrong.
Confident and wrong is the worst combination. It starts hallucinatory policies that don't even exist. It misses vital safety warnings in the manuals. It tells a part-time employee they have full medical coverage when they definitely don't. And the engineers are left scrambling, wondering, it worked in the demo, so what happened?
What happened is they fell into the RAG gap.
The RAG gap. And that is our exact subject today. We are tackling this massive chasm between a working prototype and a production-grade system when it comes to retrieval augmented generation.
RAG.
Yeah, RAG. And folks, if you are building AI or buying AI or just worried that AI is going to take your job, you really need to understand this gap.
Because the way we are closing it isn't just by, making the model smarter.
Yeah.
That's what everyone thinks. They just say, oh, we'll wait for GPT-5.
Right. The model will fix it. We hear that constantly.
But the model won't fix it. Today, we are deconstructing a blueprint, an engineering approach that fixes the data before the model ever even sees it. We're talking about the Agentic RAG blueprint.
This is some heavy-duty stuff today. We are talking about intelligent document parsing that reads like a human semantic chunking that understands vibes and swarms of AI agents that annotate your data like a team of hyperactive librarians.
It is a total shift. It's moving from search to actual understanding. And it all starts with a concept that I found, honestly, absolutely terrifying in the source material. They call it silent failures.
Silent failures. I kind of love that term. But yeah, in engineering, that is the stuff of nightmares.
It is the absolute worst case scenario. Look, if your server crashes, you get a 500 error, right?
Yeah.
The screen goes red. Everyone knows it broke, so you fix it.
You get an alert on your phone at 3 a.m. It's super annoying, but it's clear.
Exactly. But with an LLM, a large language model, a silent failure means it gives you an answer. It speaks in complete sentences. It sounds super professional. It even cites a source. But the answer is factually wrong because the system failed to retrieve the right context.
So it basically gaslights you.
Effectively, yes. It confidently asserts a total falsehood. And the source material breaks this down into 3 specific ways these systems fail silently. The first one is called semantic collapse.
Okay, let's dig into this one because I think this is where like 90% of current AI projects are just dying.
I think that is a very fair estimate.
Yeah.
Semantic collapse happens because of how we currently treat text. Computers, for all their amazing power, they have a very short attention span. They cannot swallow a 100-page PDF in one single bite.
So we chop it up, we chunk it.
We chunk it. The industry standard right now, the naive way, is to just count words. We say, okay, computer, take 512 tokens.
Which is what, about 400 words, right?
Yeah, roughly 400 words. We say take 512 tokens and just cut the paper right there. Then take the next 512 tokens and cut again.
It's literally like taking a pair of scissors to a physical book and cutting it into strips without actually reading what's on the page. You're just measuring inches and cutting.
Exactly. And the source gives this perfect, painful example from an HR benefits document. So I want you to visualize this page.
Okay, I'm picturing it. Standard, boring HR font.
Right, maybe the logo in the corner.
Oh, low-res logo.
Okay, so paragraph 1, it lists the benefits. It says, all employees are eligible for the following medical, dental, and vision coverage.
Great. I want dental. Sounds promising.
Then paragraph 2, immediately below it, it's titled Eligibility Exceptions. It says part-time employees are ineligible for vision benefits.
Okay, that's crucial information if you work part-time. That completely changes the deal.
Now imagine the naive chunker are blind scissors. It is just counting tokens. 5 10s, 5 11, 5 12, snip. And it just so happens that the snip lands Right exactly between paragraph 1 and paragraph 2.
Oh, I see where this is going.
You now have two separate islands. Island A says everyone gets dental and vision. Island B says part-time employees don't get vision.
They're completely divorced.
They're strangers. So you, the user, come along. You ask the bot, I'm part-time, do I get dental?
Okay, so the AI goes to the library to find the answer.
Right, it searches for part-time and dental. But here is the real tragedy. Island A has the word dental, but it doesn't mention part-time. Island B has the word part-time, but it doesn't mention dental.
The connection is just gone. The glue is dissolved.
Exactly. So the AI might find Island B, see part-time, and say, well, I see information about vision, but I don't see anything about dental. Or even worse, it finds Island A and says, yes, everyone gets dental, because it physically cannot see the exception on the next island.
Wow, that is semantic collapse. You've destroyed the logic of the document by cutting it in the exact wrong place.
And the terrifying part is that the user thinks the answer is right. The AI thinks the answer is right, but the fundamental logic is broken. It is a systemic failure of understanding caused by a purely mechanical process.
That brings us to the second failure mode. And this one, I mean, look, I don't want to get emotional, but
Yeah.
we really need to talk about PDFs.
Everyone hates PDFs. It is the universal language of frustration.
I hate them. You hate them. But the source material suggests that AI really hates them. It calls this content extraction brittleness.
Right?
Yeah.
Which is a fancy way of saying we are losing half the data before we even start.
Half, really half. That seems super high.
Easily half. Think about what a PDF actually is under the hood. To you and me, we look at it and we see a document. We see a bold headline, a table with rows and columns, maybe a sidebar with a little helpful tip.
It's structured. It has a visual logic.
To a computer, a PDF is not a document at all. It is a print instruction. It is literally just a script that says, put the letter H at coordinate 1050, put the letter E at coordinate 1055.
So it's a painting of words. It's not actual words.
Precisely. It is a visual container. It has absolutely no idea that those letters form a word or that those words form a paragraph, and it definitely does not know that those lines form a table.
So when you run a standard text extractor on...
It just grabs anything that looks like a letter from top left to bottom right.
So if I have a two-column layout, which is everywhere in corporate docs...
It reads the first line of the left column, then it jumps across the void and reads the first line of the right column, then goes back to the second line of the left column.
It just garbles it. So you get something like the quick Brown Fox quarterly earnings report jumps over the down 5%.
Exactly. Complete gibberish. And tables, forget about it. A table becomes a stream of pure nonsense. If you have plan A is $50 and plan B is $100, the extractor might just give you plan A, B, 5100. The meaning is completely gone.
So we are feeding this garbage into the AI.
We were essentially lobotomizing the AI. We are feeding it word soup and expecting it to give us Shakespeare. If you lose the structure, the tables, the headers, the footnotes, you are losing 30 to 50% of the actual usable information in a corporate document.
That is terrifying, but it explains so much about why these bots fail so often. They aren't dumb, they're just blind.
They are working with corrupted data from step one.
Okay, so we have semantic collapse, which is bad cutting. We have extraction brittleness, which is bad reading. And there is a third one, missing semantic context.
This is what the source calls the floating chunk problem. Even if you cut the text perfectly, and even if you read the PDF perfectly, chunks are still lonely.
Lonely? What do you mean lonely?
They're isolated. Let's stick with the insurance example. You have a paragraph about deductibles on page 5, and you have a paragraph about out-of-pocket maximums on page 10.
In the real world, those two things are married. You cannot calculate your financial cost without knowing both.
Correct. But in a vector database, which is where we store all this stuff, there are just two floating dots in space. They have no idea the other one exists.
So if I ask the system, what is my total financial exposure?
The system finds the deductible chunk. It says, here is your deductible. But because there is no rope tying it to the maximum chunk, it doesn't retrieve it. The answer is factually true. That is your deductible. But it's practically useless because it is incomplete.
It answers the exact question you asked, but completely fails to answer the question you actually meant.
That is the perfect way to put it. It lacks the connective tissue that a human brain has naturally. When you read a book, you remember what happened in chapter 1 while you're reading chapter 5.
Right.
The AI doesn't do that.
All right. We are sufficiently depressed. The system is broken. The scissors are dull. The PDFs are hostile. And the chunks are lonely. Let's fix it. The blueprint introduces a tool to start fixing this, called Dockling.
Yes, it's an open source tool from IBM. And I really love the philosophy here because It treats a document like a crime scene.
A crime scene.
It doesn't just walk in and start grabbing things willy-nilly.
Right.
It investigates first, it performs an audit.
This is the adaptive pipeline selection that was mentioned in the source.
Right. Before it extracts a single letter, Dockling looks at the file and asks a series of questions. Is this a scan or is it digital? Are there tables? Are there images? Are there complex math formulas?
Why does it need to ask, though? Why not just turn everything on? Turn on the OCR, turn on the formula reader, just hit it with everything.
Cost and speed. Optical character recognition OCR is incredibly expensive computationally. It is basically running a heavy vision model over every single pixel of the page. If you run OCR on a 100-page digital contract that already has native text in it, you're just burning money for no reason.
It's like hiring a translator when everyone in the room already speaks English.
Exactly. So Dockling is smart. The source gives a tailor two documents. Document A is a scanned receipt or maybe an old benefits flyer from the 90s. It's just a picture. Dockling sees this and says, okay, activating OCR, activating table recognition, deactivating formula enrichment because, well, receipts don't usually have calculus on them.
That's smart. It brings the heavy machinery only when it's actually needed.
Contrast that with document B, a digital scientific paper or a modern contract. Dockling says, okay, text is native, no OCR needed. I can just read the code directly. But then it sees a bunch of math symbols.
Right, the formulas.
So it activates formula enrichment. This ensures that E equals MC squared doesn't turn into EMC2 or some garbled string of text. It actually preserves the meaning of the math.
So it tailors the specific tools to the specific job.
And the result is that you get clean, structured data. You get tables that are actually represented as tables with rows and columns, not just word soup. You have solved the extraction brittleness problem. You finally have high-fidelity data.
Okay, so we have clean data now. Now we have to cut the pie. We have to solve the semantic collapse problem, the bad scissors. The blueprint proposes something called the hybrid chunker.
This is where we solve that island problem we talked about earlier. The hybrid chunker moves beyond those fixed windows that every 512 tokens rule, and it uses three core principles. And the most important one is moving from simple counting to vibes.
Vibes. We're back to vibes.
I am serious. It is about the feeling or the topic of the text. But let's start with principle one, which is structural awareness.
Which means what exactly?
It means it respects the boundaries that the human author put there in the first place. It will never split a sentence in half. It tries really hard not to split a paragraph in half. If there is a heading, it glues that heading to the text immediately below it.
So vision benefits stays permanently attached to the actual list of vision benefits.
Right. No more orphaned headlines. It seems totally obvious, but naive chunkers just don't do this. They just chop blindly.
Okay. Principle 2. This is the vibe check, semantic continuity.
This uses a small, fast AI model to actually read the text as it flows. It assigns a mathematical value of vector to each sentence, and then compares sentence A to sentence B.
It's checking for similarity.
It asks, are we still talking about the same thing here? If sentence A is about medical copays and sentence B is about medical deductibles, the similarity score is very high. The vibe is maintained, so it keeps chunking them together. But then we hit eligibility rules. Suddenly the topic shifts from money to timelines. The similarity score just drops off a cliff.
The system sees that sudden drop.
And it says, cut here. It makes the incision exactly where the topic naturally changes.
So going back to our nightmare scenario with the HR document earlier.
The hybrid chunker sees the list of benefits, medical, dental, vision. High similarity. Then it sees part-time employees are ineligible. That is a restrictive rule. It might detect a shift there, but more likely it groups that entire eligibility block together because those sentences relate to each other way more than they relate to the next section.
It keeps the context intact. It doesn't orphan the exception.
Exactly. It preserves the entire thought bubble. And the third principle is just token awareness, which basically means don't make the chunks so massive that the AI chokes on it. But primarily the focus is on structure and meaning, not just arbitrarily counting to 512.
So we have extracted the text cleanly. We've cut it into meaningful thought bubbles. Now we need to store it so we can find it later. This is where most people just slap on a vector search and call it a day, right?
That is the naive RG approach, yes.
But the blueprint says no to that. It calls for a dual embedding strategy. Why do we need two different ways to search? Isn't one search enough?
Because human language is messy. We really have two completely different ways of searching for things. Sometimes we search for a broad concept, and sometimes we search for a very specific thing.
Break that down for me. Give me an example.
Okay. Let's say you have a toothache. You might go to the search bar and type, "My tooth hurts, what do I pay?"
Okay. Pretty common query.
That is a conceptual query. You aren't using the exact words that are in the employee handbook. The handbook doesn't say tooth hurts. It says dental emergency or acute oral pain.
So a standard keyword search just completely fails here because the exact words don't match up.
Right. This is where dense embeddings really shine. This is the standard vector search. It takes your query tooth hurts
Yeah.
and converts it into a list of numbers, a dense vector, and it looks for other vectors that are nearby in that vast numerical space.
It knows mathematically that tooth and dental are cousins.
Exactly. It captures the vibe of the question. It is fuzzy, broad conceptual matching. It understands synonyms and general intent.
That sounds perfect, though. Why isn't that enough on its own?
Because sometimes you aren't asking about a vibe. You are asking for a specific code. Does plan PPO 504 cover procedure D220?
Ah, I see.
Dense embeddings are terrible at that. They're way too fuzzy. They might see PPO 504 and say, hey, that looks a lot like PPO 502, close enough.
Which is a disaster. You get the wrong plan info entirely.
Absolute disaster.
Yeah.
You need pure precision. You need to know if that exact string of text exists. That is where sparse embeddings come in.
Is this just old school keyword search, like a Ctrl-F?
It is Ctrl-F on serious steroids. It uses a model, specifically BGE M3 in this blueprint, that has actually learned weights for 250,000 different terms.
Weights meaning what exactly?
Meaning importance. If you search the cost as $50, a standard old keyword search thinks the word "the" is just as important as $50.
But the sparse model knows better.
It knows that "the" is total garbage. It assigns it a weight of 0.
Yeah.
But $50, that is a highly specific high-value token, gives it a massive weight. So it forces the search results to actually contain the number 50.
So by combining them both,
You get the best of both worlds. The dense search casts a wide net to find the right topic, like dental coverage. And the sparse search drills down to ensure the specific details, like part-time or $50, are actually present in the text.
precision plus recall.
Exactly. You get the broad semantic understanding plus the rigid technical accuracy.
Now we get to the part of the show that really blew my mind when I read the source. We have these chunks, they are well cut, they are searchable, but they are still ultimately just text. The blueprint says, this is where we stop being librarians and start being analysts. This is the agentic enrichment layer.
This is the secret sauce. This is where we leave naive raw RAG behind forever.
We are talking about unleashing a swarm of 5 different AI agents on every single chunk of text before a user ever even sees it.
Think of it like this. In a normal system, you just throw the book on the shelf. In this system, you have 5 subject matter experts read every single page and write sticky notes all over it.
Right.
They're deeply annotating the data.
And we aren't just using a basic prompt here either. The tech stack mentions Pydantic AI. Why Pydantic? Why not just make standard API calls to an LLM like everyone else does?
That is a crucial engineering detail. If you just ask ChatGPT to summarize this, it might give you a single bullet point. Or it might give you the 3-paragraph essay. Or it might say, here's the summary colon. Or it might just refuse to answer.
It's unruly. It's unpredictable.
It is unstructured data. You cannot put that into a database column easily. Pydantic AI is like a very strict school teacher. It forces the LLM to return structured data.
How does it force it?
It defines a rigid schema. It says, I need a summary, and it must be a string. I need a list of entities, and they must be in JSON format. I need a Boolean value for is urgent. If the LLM messes up and returns a number instead of string, Pydantic catches it, yells at the LLM, and makes it do it again before the system moves on.
It keeps the robots in line.
It ensures absolute reliability. It handles the validation and the error handling automatically. So when we run these agents at scale, we know the data coming back is perfectly clean.
So let's walk through these 5 specific agents because this is what truly transforms the data. The first one is the summary agent.
This one is simple but really vital. It reads the chunk and writes a 1-sentence semantic summary. Something like this section outlines the eligibility requirements for dental coverage.
Why do we need that, though? We already have the chunk. Why do we need a summary of it?
It is not for the search engine. It is for the human and for the re-ranking step later on. When the system retrieves, say, 20 candidate chunks, it is much, much faster for the AI to read 21-sentence summaries to decide what's actually relevant than to read 20 full, dense paragraphs. It speeds up the whole thinking process.
It's the TLDR for the computer.
Exactly right.
Okay. Agent number 2, the semantic role agent. This one seems huge.
This is my favorite one. This agent doesn't actually care what the text says. It cares what the text is doing.
What is it doing? What do you mean?
Every paragraph in a document has a job. Is this chunk a definition? Is it an exclusion? Is it a benefit description? Is it a procedure?
Oh, I see the power of that immediately. If I'm asking what is excluded from my plan, the system usually really struggles with that kind of negative query.
Right. In a normal system, you search for the word excluded. It might bring up a sentence that says this benefit is not excluded. That sentence contains the word excluded, so the dumb search thinks it's a match. But it is the exact opposite of what you want.
But with the role agent,
You can just filter. You can say, show me only chunks where semantic role equals exclusion. You get 100% accuracy on the intent of the clause. You filter out all the noise before you even search.
that is surgical. Okay, agent number 3, the entity extraction agent.
This pulls out specific data points. It essentially turns plain text into a structured database. It scans the chunk, it finds medical coverage, and tags it as a benefit. It finds 30 days and tags it as a timeline. It finds $50 and tags it as a monetary amount.
So it's structuring the unstructured. It allows you to ask things like, find all references to $50.
Or find all timelines related to eligibility. Imagine you want to know every single deadline in your massive company handbook. You don't have to read the whole book. You just query the timeline entities.
That's incredibly powerful. Agent number 4, the key concepts agent.
This identifies 3 to 5 core topics per chunk. Things like waiting period medical coverage, chronic illness. This is primarily used for clustering.
Clustering, how does that help the user?
Imagine you don't really know what you're looking for. You just want to browse around the knowledge base. These concepts become your dynamic navigation menu. You say, show me everything related to waiting periods. It naturally groups the documents by theme without human tagging.
And finally, agent number 5, the detective, the cross-reference agent.
This solves that floating chunk problem we talked about at the beginning. You know, the C section 3.2 issue.
Right, where the text arbitrarily refers to something else on another page.
This agent reads the text specifically looking for those hints. Phrases like, as described in Appendix B, or subject to the terms in the fee schedule.
And what does it do when it actually finds one of those hints?
It builds a graph. It links the current chunk directly to the chunk that contains Section 3.2. So now the chunks aren't floating in space anymore. They are tied together with permanent ropes. The system can follow those ropes.
So if I retrieve the main chunk, the system automatically knows, hey, I better grab Appendix B too.
Exactly. It completely automates the flipping of the page. It ensures you never get a partial or misleading answer just because the critical info was on a different page.
So we have these 5 separate agents running concurrently on every piece of text. The source says they can process 1,000 chunks in 15 to 30 minutes.
That is remarkably fast for the sheer amount of intelligence being added. We are talking about generating rich, complex metadata for every single sentence of your corporate knowledge base.
Now, where does all this rich data actually go? We aren't just dumping this into a simple vector database anymore, right?
No, definitely not. The blueprint recommends using PostgreSQL.
Good old SQL.
Good old SQL, but heavily upgraded with the PG Vector extension. We treat these enriched chunks as first-class citizens in a real relational database.
Talk to me about the schema. What does this table actually look like?
Imagine a massive spreadsheet. You have your standard columns for content, the raw text, and your embeddings, the vectors. But now, because of those agents, you have dedicated distinct columns for semantic role entities, key concepts, and related chunkids.
And because they are in standard SQL columns, you can just query them with SQL.
Exactly. This allows for what we call hybrid filtering.
Give me an example of a query you couldn't do before but can do now.
Retrieve eligibility criteria related to part-time status.
Okay, simple enough for a human.
In a standard system that is just a fuzzy text match, you basically cross your fingers and hope the words eligibility and part-time happen to appear near each other in a sentence. In this system, it translates into a highly precise SQL query select star from documents where semantic role equals eligibility criteria and entities contains part-time.
That is deterministic. It is not guessing at all. It's looking up facts.
It is the fundamental difference between Googling something and looking it up in a database. One is probabilistic, you might get lucky. The other is exact.
And the follow feature you mentioned.
That leverages the related chunk eads column. If the system finds a chunk that says see section 3.2, it can instantly execute a split-second query to pull in the content of section 3.2 and present it right alongside the main answer.
This sounds amazing, but I have to say it also sounds extremely complex. And in engineering, complexity usually means things break. How do we know if this engine is actually running smoothly? This brings us to observability.
This is exactly where the silent failure concept comes back to haunt us. In production, RA degrades silently over time. Maybe your OCR starts failing on a weird new type of PDF the HR department bought. Maybe the embedding model drifts. You absolutely need to see inside the black box.
The blueprint introduces LangFuse for this. It describes it as seeing the invisible.
LangFuse provides deep tracing. It traces every single operation across the entire pipeline.
What specifically are we tracking here?
Everything. Token counts per agent, so you know exactly which agent is costing you the most money. Latency breakdown: is the OCR slow today? Is the database lagging? Is the summarization agent timing out?
The source gives a great trace example for a file called benefitsmanual.pdf. It took 36 seconds to process.
And LangFuse breaks that completely down. It shows 8.4 seconds were spent on summary enrichment, 2.1 seconds on dense embedding.
Sure.
It lets the engineer see exactly where the time went.
That is crucial for debugging. If the system feels sluggish to the user, you know exactly why. You can say, oh, the entity agent is hanging up, let's reboot that.
And it tracks silent errors too. If the entity extraction fails on a specific document type, you see it on a dashboard immediately. Instead of waiting for a user to email you complaining this isn't working, you get an automated alert saying enrichment failed on document X. You can fix it before anyone even notices.
Now let's talk about where this whole setup actually lives. The blueprint heavily emphasizes a local-first infrastructure. We are talking Docker, Alama, Minio. Why not just put this all on the cloud and save the headache?
3 massive reasons: privacy, cost, and latency.
Privacy seems like the biggest one for corporate data, right?
Without a doubt. If you are dealing with HR records, legal contracts, or unreleased financial data, you simply cannot send that data to an external API like OpenAI. You do not want your proprietary secrets training someone else's model. With the stack, the documents never leave your physical infrastructure. It runs on your own servers safely inside your firewall.
And cost?
No per token API fees. If you decide to reprocess your entire archive of 1 million documents, you aren't paying OpenAI a small fortune. You are just paying for the electricity to run your own GPUs.
And latency.
No network round trips. The model is sitting right next to the database on the same rack. It's incredibly snappy.
Okay, we have built the machine. We have the fancy chunking, the agents, the SQL database, the observability. Does it actually work when push comes to shove? Let's look at the real-world impact. The source describes a scenario called the chronic illness showdown.
This is the ultimate stress test. If the user asks, I'm part-time and have a chronic illness, what coverage options do I have?
Let's play out the naive RAG result first. The system most companies have today.
The naive system searches for part-time and chronic illness. It retrieves a bunch of random disjointed chunks. It finds a generic definition of part-time. It finds some boilerplate exclusions. Maybe it grabs a random chunk about retirement plans because it happens to mention illness in passing.
And the user experience for that.
The user's totally confused. They get a giant wall of text. They have to piece it together themselves thinking, okay, this says I'm part-time, but does that mean I actually get coverage? And this exclusion down here, does it apply to my condition? It is a puzzle. The AI basically threw a library book at their head and said, good luck.
Now the Agentic RAG result. Walk us through the specific steps the system takes.
Step 1, dense search gets 20 candidate chunks. It casts a wide conceptual net.
Okay, broad search.
Step 2, it filters by role. It says, I only want chunks that are tagged as eligibility, benefit, description, or exclusion. Throw away the retirement stuff immediately. Throw away the generic definitions.
Nice. It's focusing in on the actionable stuff.
Step 3, it re-ranks by entity. It actively prioritizes chunks that explicitly mention the entities part-time and chronic illness.
So the absolute best matches float right to the top.
Step 4, the detective kicks in. It follows the references. It sees that out-of-pocket maximums and the appeals process are linked to those specific coverage chunks, so it pulls those in too, just in case.
And the final answer it gives the user.
Highly structured, actionable advice. It says you're eligible for medical because you work more than 20 hours. Chronic condition X is covered under Section 4.2, but note that experimental treatments are excluded. Your specialist copay is $50. Here's your out-of-pocket max.
That is a massive difference. One is a messy search result. The other is basically a consultation with an expert.
Exactly. It moves from, here are some documents you might like to hear, is the exact answer to your specific situation. It respects the user's intent, and it respects the document's original structure.
So bringing this all together, what are the core key takeaways here for the listeners?
First, chunking is the absolute foundation. If you get the chunking wrong, if you cut the text in the middle of a vital thought, no amount of smart AI down the line can fix it. Bad chunking simply equals bad RO.
Second takeaway.
Enrichment is worth the latency. It might take 30 seconds to fully process a document with all these agents. That sounds slow in the world of computers, but that 30 seconds of prep time pays off every single time a user runs a search. It is an investment in your metadata.
It's essentially measure twice, cut once, but for data processing.
Exactly.
Right.
And finally, observability is non-negotiable. You have to be able to see the silent failures to fix them. You simply cannot improve what you cannot measure.
This has been a really fascinating look under the hood. We started with the RAG gap, the huge disappointment of current systems, and walked through a comprehensive blueprint that uses rigorous engineering, not just AI magic, to close that gap.
It really highlights that building AI systems is still at its core systems engineering. It's about reliable pipelines, data structures, and observability. The LLM itself is just one component of a much larger machine.
I want to leave you, our listeners, with a final thought. We have been talking a lot about moving from search to understanding. In the past, search engines just matched words right. They didn't know what a benefit was. They just knew the literal letters, BENEFIT.
Right, they were just matching visual patterns on a page.
But this system we discussed today, it knows what a paragraph actually does. It knows its role. It knows that $50 is money. If the system can understand the role of a paragraph, what happens when it starts understanding the intent of the author?
That is the real next frontier. When the system can look at a text and say, this clause was written to be deliberately vague, or this policy directly contradicts the one in the other handbook, that is when we move from simple retrieval to actual reasoning. That's when the AI becomes a true partner, not just a search tool.
Something for you to mull over as you look at your own organization's data. Is it just being stored away, or is it actually understood?
The difference is everything.
Thanks for listening to this deep dive. We will catch you on the next one.
See you next time.